Hi everyone! Today we're going to wrap up chapter 18. So today we're going to discuss Gibbs free energy under non-standard conditions. So previously we discussed how to calculate Gibbs free energy under standard conditions. So the partial pressure of a gas is 1 atmosphere, the concentration of a solution is 1 molar, or the temperature is 25 degrees Celsius. However, in most reactions, we're not at standard conditions. So for example, we might be at a different temperature, maybe the partial pressure of a gas isn't exactly 1 atmosphere, or the concentration of a solution might not be exactly 1 molar. So in order to calculate Gibbs free energy under non-standard conditions, we need to add a factor that will account for those differences. So Gibbs free energy under non-standard conditions is represented here. So we don't have that little degree symbol that indicates standard conditions. And that will equal delta G under standard conditions when the reactants and products are in their standard states. So the temperature is 25 degrees Celsius, the partial pressure is 1 atmosphere, or the concentration is 1 mole per liter. Now under non-standard conditions, delta G will equal delta G at standard conditions plus RT times the natural log of Q. So R here is equal to 8.314 joules per mole Kelvin. And then temperature is, whatever our new temperature is. And then remember that Q is equal to products over reactants. So here we're assuming again that we're not at equilibrium or we're not at standard conditions. So also remember in our reaction quotient, we could use concentration or pressure, so it just depends on what we're given. Now at equilibrium, delta G will actually equal 0. That's a situation where K, our equilibrium constant, is equal to 1. So in your textbook, there's this diagram that shows the vaporization of water. So we're going from the liquid state to the gas state, and vice versa. So we could also go in the other direction because it's a reversible process. Now, if we write out Q for this situation, Q, remember, is similar to the equilibrium constant, where we're only going to include gaseous products and reactants or aqueous products and reactants. We don't include pure liquids or solids. So for this transition, we would only include the pressure of the gaseous water. So we don't include the reactant in our reaction quotient. So keeping that in mind, let's say that we start with all liquid, so we don't have any gas. That means our reaction quotient will be 0. And then let's say we do start to see some evaporation. Under the conditions shown here, water will evaporate spontaneously, which means that delta G is negative. So in our free energy here versus the pressure of gaseous water, we have a trend towards equilibrium. And then at equilibrium, delta G is equal to 0. So Q is equal to K. And then let's say we start with all gas. So if we have just gas and no liquid, Q is equal to 1 because we have all product. Now, under equilibrium conditions, remember if one direction is spontaneous, the other direction is non-spontaneous. So if the gaseous water starts to condense, that's going to be non-spontaneous, or delta G will be positive. All right, so this is just demonstrating the different situations we might have for a process. So again, remember equilibrium, or at equilibrium, Q is equal to K and delta G is equal to 0. But also you'll notice that at equilibrium, we're not at standard conditions. The pressure of the gas is not 1 atmosphere, so we're at a different pressure. All right, so let's do a practice calculation to see how we can calculate delta G at non-standard conditions. So let's consider this reaction at 298 Kelvin, where 2 moles of nitrogen monoxide react with 1 mole of oxygen to produce 2 moles of nitrogen dioxide, and everything is in the gas state. We're also given delta G of the reaction under standard conditions, so this is equal to negative 71.2 kilojoules. So we're asked to calculate delta G of the reaction under non-standard conditions, which are given below. So we're given the partial pressures of each of the gases. So the partial pressure of nitrogen monoxide is 0.1 atmospheres. The partial pressure of oxygen is also 0.1. And then the partial pressure of nitrogen dioxide is 2 atmospheres. And then we're asked, is the reaction more or less spontaneous under these conditions than under standard conditions? So I think the first thing we need to do is write out our equation for delta G under non-standard conditions. And remember, this includes that reaction quotient Q. So maybe the first thing after that is to write out our expression for Q. So remember, this is equal to products over reactants, and in this particular scenario, we're given partial pressures. So let's put the partial pressure of the product in the numerator. And remember, we also need to include any coefficients as exponents here. So we're going to square the partial pressure of the product. And then in the denominator, we have the partial pressure of our first reactant, nitrogen monoxide. That also has a coefficient in front of it, so let's square that. And then we have the partial pressure of oxygen. And the coefficient for oxygen is just 1, so we'll leave it as it is. Okay, so now we'll plug in our values for each of the partial pressures. And I'm leaving out the units here because the reaction quotient and the equilibrium constant are unitless. Okay, and then if you ever want to pause the video to do the calculation on your own, you can. So when we do plug this into our calculators, we get a value of 4 times 10 to the third for the reaction quotient. Okay, so now we can plug everything in to our equation for delta G. So delta G of the reaction will equal delta G of the reaction under standard conditions, which we saw was negative 71.2 kilojoules, but I'm going to convert this to joules because remember the gas constant is in terms of joules. So I want to make sure that we have the same units across the board. So I'm just going to multiply that by 1,000 to get it into joules. All right, and then we're going to add the gas constant, which is also in joules per mole Kelvin, times the temperature, which we were told is 298 Kelvin. And then we're taking the natural log of 4 times 10 to the third. So that's our oh, my pen stopped working. That's our reaction quotient there. There we go. All right, so I think the first thing I'm going to do here is calculate the second portion of the equation because that will make my life a little bit easier. All right, so we'll leave the first part of the equation the same. And then the second part of the equation, we should end up with 20.5 times 10 to the third joules. And this is not correct scientific notation, but I wanted to write everything in 10 to the third because that will make it easier to do our addition here. All right, so when we add those two values together, we end up with negative 50.7 times 10 to the third joules. But we do want to compare this value to our standard condition value. So that's in kilojoules. So I'm going to convert our delta G of the reaction to kilojoules. So we're going to divide that by 1,000. And when we do that, we get negative 50.7 kilojoules. Okay, so now let's compare that value to our value under standard conditions, and we'll determine if the reaction is more or less spontaneous under non-standard conditions. All right, so delta G of the reaction under non-standard conditions, given above, is equal to negative 50.7 kilojoules. And then we were told that the Gibbs free energy of the reaction under standard conditions was equal to negative 71.2 kilojoules. Okay, so which one is more negative? Because that will be the more spontaneous process. So it looks like delta G of the reaction is more negative under standard conditions. So that means that the reaction with these given partial pressures is less spontaneous because it's less negative. So the reaction under non-standard conditions given above is less spontaneous than under standard conditions. Okay, and that kind of makes sense if we're looking at the partial pressures that we were given. We don't have a lot of the reactants, so nitrogen monoxide and oxygen are both fairly low in pressure compared to the product, which is really high in pressure. So that means the reaction has already proceeded towards products quite significantly. So under these conditions, the reaction isn't going to keep going to a significant extent because we're running out of reactants. Now, if we had higher pressures for the reactants, then the reaction would be more spontaneous because we're trying to go towards products. Now you'll notice we still have a negative delta G of reaction under non-standard conditions. So it's still spontaneous, it's just not quite as spontaneous, and that's due to the fact that we have a lot of product and not a lot of reactants left in order to produce more product. So hopefully that makes sense, but it's always good to kind of go back and double check if your answer makes sense conceptually. So, always try to think about these problems on a deeper level rather than, just kind of plugging and chugging because, it's important to understand the background too. All right, so One last thing before we do our worksheet problem 10. Remember that delta G at equilibrium is equal to 0. So that's what we said earlier. So if we set the equation we just used equal to 0, and I'm going to write K here instead of Q because we're assuming we're at equilibrium, we can rearrange that equation to give us delta G of the reaction at standard conditions, and that's equal to negative RT times the natural log of K. So this is another way that we can calculate the Gibbs free energy under standard conditions. So just a couple of things to keep in mind. When K is less than 1, so we have a really small equilibrium constant, and let's kind of write out what that is just so we remember. So products over reactants. When we have a really small value of K that's less than 1, that means we have a lot of reactants. And we're assuming the reaction has already occurred here. So if we have a lot of reactants, that must mean the reaction doesn't proceed in the forward direction to a significant extent. Now, if we think about that mathematically, when we take the natural log of a small value of K, we get a negative value. And you can even just plug in like natural log of 1 or something. You should get a negative value, and that's going to cancel with this negative value at the front, which gives us a positive value. So when K is less than 1, delta G is positive. And we know from before that when delta G is positive, we have a non-spontaneous process. So what this tells us is that the reverse reaction is spontaneous. So for instance, let's say we have A going to B. So if delta G is positive for this forward reaction, A to B, that means it's non-spontaneous. But B going to A is spontaneous. All right, so what that also tells us is that nothing's going to happen for this reaction unless there are products present, because the reverse reaction is the spontaneous reaction. Now, if K is greater than 1, then the natural log of K will be positive, and then we multiply that by a negative, which gives us a negative value of delta G. And we know that when delta G is negative, that means the reaction is spontaneous. The other way to think about this, if we have a large value of K, that means we have a ton of products. So that means the reaction in the forward direction is spontaneous. It occurs to a significant extent. And then if K is equal to 1, then the natural log of K will be 0. So delta G will be 0, and the reaction is at equilibrium, like we said before. Of course, in this particular case, the reaction will be at equilibrium under standard conditions. All right, and here's a few examples of some free energy charts, kind of showing the same idea. So on the upper left, we have a small value of K, which again means we have a ton of reactants. And this reaction will only occur if we have a lot of products. So under standard conditions, we're going to assume that the pressure of A is equal to the pressure of B, which is equal to 1 atmosphere. So Q will be equal to 1. And we're going to see that the reaction proceeds in the reverse direction. So the reverse reaction is spontaneous. So remember, if Q is less than 1, if K is less than 1, but Q is equal to 1, we're trying to, or the reaction's trying to proceed in a manner that's going to bring the reaction quotient towards that value of K. So we're trying to decrease the number of products. So we're trying to go back in this direction so that Q will equal K. Now, what if K is greater than 1? If K is greater than 1, that means we have a lot of products. So that means that the reaction is spontaneous in the forward direction. Now again, under standard conditions, if Q is equal to 1, we're trying to bring Q closer to K. So we're trying to go in the forward direction to get to equilibrium. And then if K is equal to 1, we're at equilibrium because delta G will be equal to 0. And the reaction isn't going to proceed in any particular direction or favor any particular direction. So you'll notice in this graph on the bottom, we have a very symmetrical parabola. But in the upper left, the parabola is kind of shifted towards the left because we're kind of going in that direction. But then on the upper right, the parabola is kind of shifted towards the right because we're trying to go in that direction for the reaction to get to equilibrium. So these charts are a little complicated. There might be an easier way to express all of this, but let's do a practice problem so we can kind of see mathematically how this all works out. So on worksheet problem 10, we're going to consider the reaction where iodine reacts with chlorine to produce iodine chloride. And we're given the value of K, which is 81.9, so K is greater than 1. And this is at 25 degrees Celsius, so standard conditions. So now let's go back and kind of look at our chart for K greater than 1. So remember, this tells us that the forward reaction is spontaneous. Okay, but we're going to actually calculate delta G for the reaction at 25 degrees Celsius under each of the following conditions, and then we'll kind of compare them. So we're going to calculate delta G under standard conditions, at equilibrium, and then in the last situation, we have different pressures for each of the products and reactants. Okay, so let's start with A. If we're at standard conditions, delta G, let me find my notes. There they are. Delta G of the reaction will equal negative RT ln K. So remember from before we said that delta G of the reaction under standard conditions can be calculated using this equation. So this is super easy. We're just going to plug in the gas constant, 8.314 joules per mole Kelvin. And then the temperature, and we're at 25 degrees Celsius. So if we do a quick conversion here, that's equal to 298 Kelvin. And then we're going to take the natural log of K, which is 81.9. All right, so once we calculate that, we should end up with a value of negative 10,914.9 joules per mole. Now remember, delta G is usually expressed in kilojoules. So we can convert this value to kilojoules. So we're just going to multiply by 1 kilojoule over 1,000 joules. And that will give us negative 10.9 kilojoules per mole. Okay, so under standard conditions, is this reaction spontaneous? Yes, it's negative, right? And that makes sense with what we saw earlier. If K is greater than 1, then delta G is negative and the forward reaction is spontaneous. So it all lines up, which is perfect. Now, what about at equilibrium? So remember, at equilibrium, delta G under non-standard conditions will equal 0. So that means that we can set this equation equal to 0. And we're going to plug in K here because we are at equilibrium, so we can use the equilibrium expression. Now, we just calculated delta G. So delta G was negative 10.9 kilojoules per mole. But remember, that's equal to the negative of RT ln K. So actually, if we plug that in, we get 10.9 kilojoules per mole. So this actually all cancels out to 0 anyway. So just remember, at equilibrium, delta G is always equal to 0. So you don't even have to do this calculation we just did to prove that it's equal to 0, but I wanted to show you that it is. But you could have just written delta G is equal to 0 at equilibrium, because we already know that. All right, so now what about under these conditions where the partial pressure of iodine chloride is 2.55 atmospheres, the partial pressure of iodine is 0.325, and the partial pressure of chlorine is 0.221. All right, so if we want to calculate delta G of the reaction, we're going to need the calculated Gibbs free energy under standard conditions from earlier. And then we'll also need to determine what our reaction quotient is because we're not at standard conditions any longer. All right, so Q, let's set that up, will be equal to the partial pressure of the product. And there is a 2 there, so we're going to square that. And then we're dividing by the partial pressures of each of the reactants. And both of their coefficients are 1. So we're just going to leave them as is. And then we'll plug in the values for each. So the partial pressure of our product squared over the partial pressure of each of our reactants multiplied by each other. And when we plug this into our calculators, we should get a value of 90.5. Okay, so now we have everything we need to plug this into our equation here. So remember earlier we said that, let's see, the delta G of reaction was negative 10.9 times 10 to the third joules per mole. And you could plug in the more exact number there if you want, but remember we want this in joules because we're going to add the gas constant in joules per mole Kelvin. And again, the temperature is still 298. And then we're taking the natural log of 90.5. Okay. So if we do this calculation, and I'm just going to double check my work here because I'm not sure if my answer is right. So 8.314 times 298 times the natural log of 90.5. All right, so that gives us, let's see, I'm going to rewrite the first part of the equation. Let's see, so we get plus 11.2 times 10 to the third joules per mole. Okay, and so now let's take negative 10.9 times 10 to the third and add that answer. And we should get about 262 joules per mole. Okay, so is this reaction spontaneous at these conditions? No, because delta G is positive, right? So that tells us that under these conditions, the reaction in the forward direction is not spontaneous. Okay. All right, so remember that the equilibrium constant can change based on temperature. And down below, we can actually write an equation to show the temperature dependence of the equilibrium constant. So if we combine these two reactions here, so we can set, here I'll write it up above, we can set delta H minus T delta S equal to negative RT ln of K. And if we divide both sides by negative RT, we end up with the equation shown here, where the natural log of K is equal to the enthalpy change of the reaction over the gas constant times 1 over temperature, plus the change in entropy of the reaction over the gas constant. So notice that this equation is in the form of y equals mx plus b. So what's great about this equation is we can graph the natural log of K versus 1 over temperature, and that will give us a straight line where the slope is equal to the change in enthalpy for a reaction over the gas constant, and the y-intercept is equal to the change in entropy of the reaction over the gas constant. So let's see what that would look like. All right, so if we plot the natural log of K versus 1 over the temperature, so inverse temperature, we'll have a positive slope, potentially, and the slope, m, will equal the enthalpy change for a reaction over R, and then the y-intercept, B, will equal the change in entropy for a reaction over R. So, for instance, let's say the slope is equal to 100. I don't know. We'll just set it equal to that. We can always rearrange the relationship here to solve for delta H of the reaction. And we could do the same up above for the y-intercept in order to solve for the entropy change of a reaction. So I'm not going to go too much further into this because later on we'll do a lab where we're going to find the equilibrium constant for a reaction at different temperatures. And then we're going to plot that data and figure out what the enthalpy of the reaction is and what the entropy of the reaction is. So we'll get some experience and practice with this later on. But this is the end of chapter 18. So we're going to start chapter 19 next. And chapter 19 is a little bit different. We're kind of moving away from thermodynamics. It's still applicable, but we're going to start talking about electrochemistry. And electrochemistry is really important. So if you've ever used a battery, you have used energy from electrochemical reactions. So we'll talk about that in the next lecture. So I will see you in that next video.